Okay, so Nadina had pointed out a really good correction that I made, which is important for you guys to see. So you can see, if you guys look at the old version of the syllabus, you will see that there was a typo. It had reading week is October, which doesn't make any sense, obviously, right? So this is, if I just scroll down all the way to the bottom, and she was saying that in order to facilitate your settings, so that like if you want to read ahead, you know where we are in the material, that it's important, right, to know what the actual correct days are. So before it's at October here, but obviously you guys know reading week is in June, right? So I was just making that correction. That way you know that the furthest we'll actually go before reading week would be obviously week 5, but that's obviously subject to how quickly we go, right? It may, like, for instance, it may or may not be the case that we see, right, this stuff in the midterm. It depends on how fast we go. Okay, cool. Just wanted to point that out because obviously that can be confusing if you look at the syllabus and you're seeing a time that already passed for reading week. Okay, so yeah, so if you want to join audio, so obviously I have mine at the top, but it should be somewhere here basically, right? So just kind of join audio, check your audio settings here. When you are joining, check your audio settings, right? It might be that you haven't turned it on, right? So make sure you have it on. Okay. So since it's Thursday, I'm guessing that most of you so far have gone to tutorials, but some of you may not have, because I think there's one on Friday maybe, right? So, but for those of you who looked anyways and you haven't had a tutorial, you will see that the questions on the tutorial worksheet really actually span slides 10 and 11. It's really about population and sample, so very simple, very quick worksheet. But the quiz next week will encompass the population and sample stuff, but also variables, like what is an ordinal variable, what is a nominal variable, right? So things like that. So that's really the week 1 content. So if you're confused about any of the stuff in today's lecture, please let me know and I will go back. Okay, so just to reiterate, obviously we talked about the population and the sample, and we said that the sample is really actually smaller than the population a lot of times. And that's because it's difficult to actually acquire observations on the set of your population when it's big, right? So imagine, for instance, with Census Canada, you never get the entire sample because you would have to actually sample all 40 million Canadians, but you hope that enough people fill it out to get some kind of reasonable estimation of like things you might want to study about the demographics, right? But of course, you may never get the entire population. So your sample can be as big as your population if you sampled every single unit, but most of the time it's smaller than it because you just don't get the entire sample, so you don't get the entire population. And this will have ramifications later on because we will ask ourselves, yeah, absolutely. So the subject, so this means here, you mean basically, are you referring to like this part here? How do you say your name, by the way? Is it Atra? Okay, so cool. So Atra's asking like, what do you mean by subjects basically, right? So first of all, I should backtrack a bit and say that really when you specify a population, you have to know what the subjects are basically. So the subjects, to be clear, is anything you want to actually study a phenomenon on. So if you have a question you want to address, the units are the things you want to actually observe the question you're asking on, basically. Now, a lot of the times, the subjects actually constitute people, right? Most of the time, it's individual level. So for instance, Census Canada, the subjects are people. We are interested in Canadians, but we have to be clear here. It doesn't have to be people. It can be really anything. So for instance, maybe you want to know the average number of children in a household. And that means the house, if let's suppose, for instance, in Canada, we want to know what's the average number of like kids in a family. So now the units are not individual level, the units are now families, basically, if you want to study the average number of kids. Oh, can anyone hear me? Or am I still cracking up? Let me know if I'm cracking. Okay.
I can hear you just fine.
Oh, that's the first time someone spoke up. Cool. But if anytime you guys feel like you really want to ask a question, feel free to like open your mics and we can make it interactive. Okay, cool. So I just wanted to say that this, in the example I gave with the families, you can imagine that if you want to know how many kids a family has, that your units are family. It's not people, right? So first you have to know what the question you want to ask is. And when you ask that question, you have to identify what the units are basically. Sometimes it could be schools. If you want to know, for instance, the average GPA across different schools in Ontario, then the unit's now school. So it really depends on the question you want to ask. First, you need to ask the question, and then you actually think to yourself, what are the units you're actually studying basically. So let me address the question. So the study is to identify political affiliation. Would this subject be only adults? Yeah. So if your study, Brittany, is to identify a political affiliation, you cannot vote if you're under the age of 18, right? So you're looking at adult Canadians and it's at the people level, right? But really you're only interested in like adult Canadians because you cannot vote if you're under the age of 18, right? So that's a good question to ask. You have to really specify your question. And once you specify the question, only then does the units actually fall into place basically. So what's the difference between the subject and same? What do you mean same? What is same, Dominique? Do you want to maybe clarify the question?
Sorry, I mean sample.
Oh, yeah. So the subjects are the thing you want to study. The subjects remain the same even within the sample, right? So to go back to Brittany's question about like political affiliation, the subjects are still going to be in your sample adult Canadians. It's just you're not going to be able to sample every single adult Canadian. So this means that the units remain the same between the sample and the population. It's just that the size is actually going to be smaller in the sample because you cannot get every member of every unit you want to study basically. So in that way, the subjects don't actually change between the population and the sample. What changes is actually the number of subjects you actually get to study, right? So that's really the distinguishing difference there. And to address Brianna's point, no, your samples, your subjects do not need to only be an individual. It could also be an object, like you said, exactly. It could be an object, it could be like cars, whatever you want to look at. It's not limited to people. It's just, you can imagine in social sciences, a lot of times we concern ourselves with people. So a lot of the examples might be people, but we should not assume that it's the only thing we could study. Yeah, you would have to mention the adult Canadians when you refer to political affiliation, because we need to keep in our mind that we are not looking, it's more than just the actual, you're not looking at the people under 18 because they don't qualify to vote, right? So you need to be very specific as to who your subjects are. Specificity matters. And in the case of political affiliation, you need to make it clear, you're looking at the adult Canadians, not just any Canadian, because it's not any Canadian. So yes, Alba, the size of the sample is always smaller than the population. The only exception is if your population is so small that you can sample every single unit, in which case the sample is the exact same size as the population, but the sample will never be bigger than the population. It can never be, basically, right? So for the subject, we state that what we're studying in the, yeah, so when you first address your question, then the units you're studying comes from that, basically. So the population, to address the population, is a total set of the subjects. It's a subject is only as small as one unit, the population, right? But the population encompasses every single total set of subjects, right? So for instance, if my subject is adult Canadians, or if I want to know, for instance, political affiliation, then in this way, I'm looking at adult Canadians, as Brittany asked, right? But one subject is one adult Canadian. The population is all adult Canadian. So the distinction is you're looking at the collection of subjects in a population, whereas one subject constitutes just one member of that population, basically. No worries. Any other questions? Exactly. So H is saying, let's suppose you're interested in, let's say, manufactured automobiles. Then you're in this case, your subject is one car, basically, exactly. And the population would be all the set of cars you're looking at, basically. So the subject is really only one member of the population, right? It's really like this, the set of all subjects constitutes your population. But of course, you cannot sample every single subject sometimes because your population can be too big. imagine there are 40 million Canadians in Canada, right? And really, I guess if you actually cut out those that are under 40, maybe you have 25 million adults. But the thing is that you cannot sample that many people. It's impossible. It's a logistical issue. So you can only get a sample of your subjects, but the sample itself is still a collection of your subjects. It's just smaller than the population because you didn't sample everyone, basically. Any other questions? So that's really the basis of your worksheets this week, by the way. So the reason why in the family example, your subject is not the kids is because the question asks the following, right? What is the average number of kids in a family unit, basically? So the question I'm asking is really about the family unit, basically, right? So in which case, the subject itself is not the kids, it's really actually family unit. Like, what is the average number of kids in a given household, basically? So a census is actually a census is a population, basically. Your goal is exactly that. Your goal is to actually sample the entire population. And in fact, Census Canada will send out as many reminders as possible, right? To really get as many people to fill out the survey as possible. It's called census because they want, in theory, everyone to answer the survey, but there's a feasibility issue. In practice, that you just never know what the answer to, you don't know what that is. In reality, you cannot get everyone. But in theory, you definitely want to survey the entire population. Now, this has implications in statistics, basically, right? Statistics is really a science of uncertainty. Where is the uncertainty coming from? The uncertainty comes from the fact that you really cannot actually measure every single person in the population. So there's uncertainty from that alone, basically. That's the uncertainty, right? The fact that we cannot capture everyone in our sample is why it's the science of uncertainty, basically. So the question is our statistics still correct if we cannot get everyone in the population, right? And there are implications as to what constitutes a good enough sample. So we feel confident that at the population level, we can still make some kind of inferences, basically. So at the sample level, we call, and you're going to see that soon in the lecture for any of you who would have had, basically, we're looking to look at statistics, which correspond to, in this case, it's always going to be a numerical value because we're looking at like quantitative methods. So we're always going to be looking at statistics. But the issue we have, right, is that obviously we're limited by the fact that the statistics is done on a sample basis, but it's going to be a numerical value in the scope of this course because we're interested in obviously capturing things about like averages or something, right? So most of the time it will be a numerical value, but there is a specific definition, Eileen, for there's a specific definition for what this numerical value happens to be for the sample, right? We have to distinguish in our mind a numerical value of the population and the numerical value of the sample, right? So which we're going to do, I think, in this lecture. But keep this question in mind, right? So we're going to look at a numerical value, but what is numerical value for the sample? It's different from that of the population, which I'll elucidate in a bit. Okay, so you can see here that the sample is a subset of the population. So just to be clear here, that means that it's going to be a subset of the number of subjects in the population, right? So it's still going to actually you're still looking at the same subjects in the population, but you just cannot sample all of them. You cannot collect all of them. And this is where the uncertainty comes from. The fact that we cannot sample every single member of the population. So we are limited by our sample in some sense, right? So for an example, a GSS asks 1,000 surveyed Americans about their opinion on same-sex marriage, right? Now, there's more than 1,000 people in America, right? So there's the issue, is that we cannot sample 400 million people. We are limited by the fact that we only sampled 1,000, right? And so this is the questions we ask. Like, how do we know that our inference is good when we didn't sample everyone, basically, right? The interest is essentially to map on the typical American's opinion on same-sex marriage, but we're going to do that based on a sample of 1,000 people. Now, obviously, there's going to be some consequences of this. The fact that your sample is so small, but we need to make sure that at least if we have a sample that's only 1,000 people, that it needs to be a good sample. So in this course, we will discuss what constitutes a good sample when we know that our sample is so much smaller than our actual population size. We need to make sure that it's a good sample at least, right? Yeah. So the other thing that you'll see in your quiz is the distinction between descriptive and inferential statistics. Does anyone know, right? So what when you think about descriptive, what do you think of? Like the definition of descriptive, how do you interpret descriptive in comparison to inferential? Yeah, descriptive is really describing data, right? Exactly, illustrating data, describing data, exactly. So Sumera is saying it's describing data as descriptive, but if you want to make a prediction, basically, this is inferential. So I'm gonna use those two examples because it really makes a lot of sense, basically, right? So the first stage of statistics is always to describe what you saw, basically, to illustrate the data. Someone else also said it's an illustration of what you saw in your data. But keep in mind, it is not a prediction, right? So we need to keep these two things in our mind to really elucidate the distinction between descriptive and inferential statistics, right? So we are not predicting at the descriptive level. We are only illustrating, as someone said, what we saw in our data. It is very much rooted in the data itself. But when you want to make a prediction, this is when you're looking at inferential statistics, right? So predicting about what? Predicting it as to what the actual phenomenon looks like at the population level. Why are we doing this? Because you don't have a sample that is the entire population. You have a sample that is a subset of the population. It is smaller than the population. And in this way, you're always going to make a prediction. If you do not have the entire population, everything you do is a prediction, basically. When you're predicting to the population level, you're making a prediction. Now the question is your prediction good? This depends on your sample. And even in the statistics you do. So we're always making predictions when we talk about inferential statistics. And the reason why we are predicting is because, right, we do not have the entire population. So the prediction must necessarily happen, right? But as many of you said, the first stage is always to illustrate or describe your data, right? This means that you are literally summarizing what you saw in the data, right? How do you do this? Well, first of all, you need to make sure that the way in which you actually summarize your data is communicable, basically, right? So people have to understand what you said, right? If you just present something in a very messy format, this is in some sense not good, right? Yeah, you cannot say, so Eileen's saying, does that mean that you can say that 85% of adult Canadians believe in heaven? No, you cannot say that, right? So you cannot say that based on what you saw in the sample, that it's true that 85% of them at the population level believe in heaven. What you can say is that we predicted that 85% believe in heaven, basically, right? Yeah, it says Eileen. Oh, good to know that's Emma. Okay, so let me look at some of the questions people have. So someone says, would you use descriptive statistics to analyze a sample? So Sarah's saying, can you use descriptive statistics to analyze a sample, but inference to analyze a population? Yes and no. So descriptive statistics is always analyzing the sample data. That's something we should keep in our mind, right? You're always analyzing. Descriptive statistics is necessarily analyzing what you saw in your sample, basically, right? So that part is correct. You are always using descriptive statistics to analyze the sample. Inferential statistics is really used to make predictions about the population, but you still need to use a sample to do it, right? Because all you have is your sample data. So you still need to use a sample to make predictions, but the predictions you're trying to make are at the population level. So this is the part where it's kind of finicky, right? So let me repeat this. Descriptive statistics is always going to happen, right, in regards to summarizing the data of the sample. But you are still going to use a sample to draw conclusions about the actual predictions of the population level. You still want to predict at the population level because your goal is always to address a question at the population level. But of course, you do not have your entire population. So what does this mean? You have to use this sample data to make inference at the population level. So this is the part where we need to kind of recognize we're always using our sample data, but the way in which we use it is different if we're making an inference or a prediction. Okay, someone else said, in the text, it is referred to as margin of error. How is that determined? So Brittany's saying you have a margin of error in regards to the extent to which your actual prediction is off, basically. And what do I mean by off? It means that like there's always a margin of error, right? As to, you know, like the range of values your prediction can take and the implications it has in regards to how good it is as right at the population, as predicting at the population level, right? That's a to be continued, Brittany. So margin of error I'll discuss in a couple of weeks from now because we don't have the tools just yet to really determine, to explain or elucidate how we determine that. But that's an important idea we're going to talk about when we get to when we really get to the nitty gritty. So no, so descriptive statistics, Emma, really is, sorry, margin of error is for inferential statistics, but that's to be continued, right? So margin of error is something we actually ask ourselves. We want to know how good our estimate is, but that's at the inferential level, because right now the margin of error corresponds to, right, how good your actual estimate happens to be, like what's the extent to which you were off, basically, and you're in prediction, basically. So when you're talking about prediction, you're always referring to inferential statistics. So this is why margin of error doesn't really talk about, it's not really pertaining to descriptive statistics, but we will talk about that soon. Not quite yet, but soon. Okay, so we want to summarize the data. That is the first line of defense. And if someone says that you really like, we want to illustrate our data, basically. Why is that? Because you, in some sense, your data tells a story, basically, right? But so if you want the data to tell a story, you have to think about how you actually present your information, right? So if I was going to communicate my ideas to a non-statistician, I would have used a lot of pictures based. People tend to like to visualize things, right? Which means that, for instance, I would probably, use graphs and right before I even use, for instance, tables. Graphs would be my first line of defense if I could, because people tend to understand when you show them patterns, right? So for instance, when you look at COVID data, people don't present tables. They present figures, right? You want to see if there's a downward decline in the caseload. You show graphs. You don't just show tables because people don't like to see it like that, right? So I would present graphs first, and then tables and numbers second, right? But I would do it in a particular way. What way? In a way that I don't lose information, basically, right? So if I, for instance, give you a graph that shows the downward trend of COVID cases in Ontario, for instance, it should not be presented in such a way that I couldn't translate this back into table format, basically. You cannot lose information when you present information, basically, right? You have to present it in a way that all the original information is still there. Right? So if I give you a graph of the cases in the case of Ontario, I can still go backwards and look at the day and the number and put it back in table format, basically, right? So if I wanted to show, for instance, COVID cases in the beginning of May to mid of May, I could obviously look at the graph and say, well, on May 1st, it was this number was this much from the graph. On May 2nd, it was that much. So I could put the graph back into table format, and I don't lose information, basically. But people tend to like to see graphs because it's nicer. And so I would present it in a graphical way so that I haven't actually lost information. This is important because you cannot falsify your data. You have to have some integrity with your data analysis. You cannot communicate things in a way that you've cheated, right? Exactly, it should be interchangeable, basically. So H is saying, when you present this information, what H is corresponding to what? I want to make sure I remember your name. I remember you saying in the first class that your name says H, but it doesn't say your actual full name. What is your full name? So I know when I'm thinking about because obviously, yeah, okay, there you go, got it. Okay, cool. So is it Hamil? How do you say it? Your name? I don't want to mispronounce your name. Hamil. Okay, cool. So you can imagine that it is interchangeable, as Hamil is saying, basically. Well, also I said in the first day of class, I tend to remember certain students' grades and names, basically. When I'm looking at boundary grades, that kind of sticks in my mind, basically, right? So that's why I kind of always ask students their names. So when I'm looking at the grade distribution, I remember, basically. Okay, so it should be interchangeable. That means that you should be able to go from the table format to the graph and vice versa. You should not lose information when you present your data, but you definitely want to present it in a way that people can digest it quickly, right? Another thing is that you can present it in tables, you can present it in numerical values too, right? So as Sarah was saying earlier, you definitely would not just present, you cannot say in this example here that at the population level, 85% of Americans believe in heaven because you only sampled 1,326, right? But you can go backwards a bit, right? So for instance, here you cannot say that at the population level, 85% of Americans believe in heaven. That's just not right, right? This is pertaining to your sample, right? But I do want to point out, right, that I want to point out the following. This is even in itself a reduced way, a reduction of your information. How is that? This is reducing it to a way that looks communicable, because I could go backwards if I wanted to. And if I just literally take 0.85 and I multiply it by 1,326, I'm going to get a particular value. And let me just compute that and not be lazy, right? So my instinct is just kind of say, it's whatever it is, but I should actually compute that. So 1326, it's about 1,127 people, right? Exactly. This is the people who said yes, they believe, right? But here's the thing. Thank you, Atra, that's nice. The students helping me to be lazy, that's good. But yeah, so you can see that but yeah, so you can see that this is the number of people who said yes, they believe in heaven. Now, obviously, I could just say, if I was a statistician, well, out of the 1,326 people that were sampled, 1,127 said yes. Or I could make it a bit easier and say, well, 85% of them said yes, right? Well, the reason why it actually making it a percentage is descriptive is because people would rather just see the percent of the total population that said yes than having to see 1,127 said yes. Because why is that? Because until you actually divide 1,127 into 1,326, you will not know the percent that said yes, basically. Right? So the reason why it's descriptive is because you have actually reduced the last step that someone has to do, because you just gave them percent instead of telling them to compute it themselves, basically. That's why it's actually descriptive. You describe the data in terms of numerical values without telling them to actually compute it themselves. Right? So I could just leave it as like 1,227, I could literally leave it as 1,127 said yes, or I could actually compute it for them and say, well, 85% of the sample people said yes, they believe in heaven. So Melissa's saying, isn't 85% an inferential descriptive? So to answer Melissa's question, yes, 85% is going to be the inferential statistics, but not quite, because it's not done, right? So this is descriptive until I actually compute something else. Until I talk about margin of errors, Melissa, 85% that estimate itself is not enough, basically. So it's an inference, but it's incomplete, right? So it's not complete as it is. I need to do a bit more to get the inference, basically. I would never talk about inference. The inference is not just the point, is not just the value alone. You need to talk about margins of errors, as was mentioned earlier, but I haven't quite done that just yet. I think it was Brittany said, what about the margin of error? So until I talk about margins of error, I haven't quite finished the inference. So I wouldn't, this is for now just descriptive, basically. It is still describing the data. I haven't quite yet made an inference, but when I do, you will see margins of errors come up, and that's when the inference is happening. That's a couple of weeks from now, though. We haven't made any predictions just yet, no. So so I will eventually make a prediction, but when I do, I will bring up margins of error, basically. So if you leave it on not computed and you put, for instance, put it in table format. So for instance, let's suppose you present a table like the following, basically. This is also descriptive. You can do the following. You can say like, you know, something like yes, no, no, right? And you could put like number of people. You can do something like, you know, 1, 1, 2, 7, and then like whatever that difference happens to be, 1, 1, or, you know, 200 and something, obviously. I'm being very lazy. So this is obviously 200 and something, approximately. Oh no. This is approximately 200 and let's say 30. I'm being very lazy, I'm sorry. Right, so this is also descriptive. It's a table format. Right? I could do this as well, basically, but I probably would not, right? But this is also descriptive because you can see this is a table format, basically, right? And which is also. But if I were going to publish a paper as a statistician, my paper would have both, would have this, but it would also have the numerical, it would also have the 85%. I would put both. And technically speaking, if I was going to publish a paper, it would contain both of those things, actually. And when you do your projects, guys, you should contain both. It will contain the table, but you should also say it in terms of colloquial, like, oh, it's 85% said whatever, right? So you should still have the table in your projects, But you will also have like the numerical value, just to, because generally speaking, a good report has both. Right? So if you're gonna, if for your projects, I'm gonna post a sample report when it gets to that point, you will see that they had both the descriptive statistic in terms of the table format, but they also had it in terms of like the percentage. It's just, you would probably have both. Cool. So I think it was, I forget who, it might have been Sarah that asked me, but you know, the question was like, is inferential statistics where you analyze the population? And I said, maybe, kind of, not complete, because you're still using the data to make predictions about the population. And here's a formal definition of that, right? So you are still limited by your data, by your sample, right? So in this way, we're still using the sample data to make inferences about the population. But the part that was correct about the statement was that we are concerned with the population at this point. You see, we need to know what is, the question is always at the population level. So even though in some sense, we are, you know, bounded by our data, we are at the inferential level, we are still concerned about making predictions about the population. So this is the thing we concern ourselves with. What does this mean, right, in this regard? Well, it means that we have to be careful about the sample we're using. And this representativeness matters, right? So you see, because we know that we cannot sample everyone in the population, we cannot get all our subjects, we have to be sure that the subjects we acquired are representative, right? So for instance, if you want to know something about Census Canada, and you look at your population and it's missing some kind of demographic, you may ask yourself if your sample is representative, and it may not be, basically, right? Well, it's not that we don't use data from the population, Emma. Your sample is coming from the population. It's just that it's not the entire population. It's only a subset of it. It's a sample, right? So your data is always coming from the population. It's just that you cannot sample every unit of the population. And so this means you're only limited by a small fraction of the population, which is a sample. And so you're always concerned with, you always want to get from the population. It's just that the problem is that you cannot get everyone from the population, right? And so this means that we need to be careful to ensure that this sample is representative. Right? Because if it's not, then any inference we make at the population level is not quite correct, right? And so this is why I said, if you are concerned with some kind of census data and you have a sample that does not reflect the demographics of the population, you may not feel confident in the prediction you made, basically. Right? That's the caveat we have here. So that's a question. So Lena is saying that, how do you know that you're off, basically? We have some tricks to determine that. First of all, our first line of defense is to ensure that our sample is representative. So how do I, first, I know I have some idea that it's good, first of all, if I sampled in a way that is actually representative based. So that's my first thing. The first thing we're going to talk about, Alina, is what constitutes a good sample, right? So there are ways to determine this, basically. The second thing is the statistics we employ. So the first thing is the sample you chose. The second thing is to ensure that your statistical method makes sense. We're not going to touch part 2 just yet. For now, we're going to talk about, like, how do we know that our sample is good based? How do we determine a good sample? That would be our first way to determine if our inference is off, is to make sure our sample is representative in some sense, right? So that's what we need to take into account, basically. We need to first ensure that our sample is good. Now, how do we know our sample is good? I'm gonna elucidate good methods to determine what constitutes a good sample, or a representative sample, basically, right? So a good sample is one that's representative, which is kind of arbitrary, but I'm going to elucidate that in a minute, right? There are ways in which we sample to ensure that our sample is actually good. It depends on how you sample, basically, right? And how do you sample? Well, it depends on what you're actually looking at. So for instance, in drug therapy trials, right, a good sample may mean that you sampled every ethnic background, every ethnic group, basically, right? So the characteristics you're looking for depends on the questions you're asking. In a lot of medical trials, that depends on the demographics, the breakdown of your sample base, because you don't want to complete a trial that is very biased in some sense, so it only works in one ethnic group, right? But in general, there are statistical methods we're going to employ in terms of sampling to determine or elucidate what constitutes a good sample? And we're going to discuss that now, right? So to be continued, you're asking a lot of good questions. How do you determine how accurate your sample is? So you can the only way you know if your sample is accurate, right, is if you sampled randomly. So I'm going to talk about the notion of randomization just in a minute, and that's how you determine if your sample is like good. But the only way you know if your sample, the only way you're going to know if your actual estimate is accurate, like at the prediction level, is if you consistently get the same estimate when you sample many samples. But that's arbitrary right now. It's not going to make any sense. But I would say that to make sure your sample is actually accurate, you kind of need to check your estimate basically. But check the estimate is a to be continued basically. But for now, we're going to say that what we're going to concern ourselves with is we're going to ensure that our sample is in some sense actually representative through the way we sample basically. If you have a specific demographic that's undersampled, well, that could be bad news because it may be that your actual estimate, if you really need to make sure that you sample certain demographics and you did not, then your estimate is, you need to state that. In your result, you need to state that your actual estimate only works on these particular groups, that it may not be generalizable to your whole population. A good statistician will state this, that you have some limitations in your inference because you may not be able to generalize to particular ethnic groups. You have to state this, right? So you don't have miscommunication. That has to be stated. And you will even see that when you guys do your by the way, when you guys do your actual self-reflection reports, you will see that some of your actual studies you choose will state this. We'll say that you cannot generalize we cannot generalize based on this data. And you will know right away that you cannot make inferences on that analysis that they did, right? Sometimes you just can't, you cannot make analysis and you cannot make inferences, and that's just how it goes, that you don't have generalizable data. And that's when it happens, but sometimes it happens and we need to know that it's the case, so we don't actually make generalizable statements. If you cannot make inferences, you just it's kind of just socks basically, right? You have to either A, find a sample that actually is representative, or B, state that your actual results cannot be generalized past your sample basically. Right, a lot of the times we cannot go beyond descriptive statistics. We are limited, and we have to, when we as statisticians realize that we cannot actually go beyond our data, we have to state this. And that happens sometimes. You cannot make inferences past your data, and we have to just admit this to people and say that we cannot generalize the population level. All we really have is an illustration of our data. That happens sometimes, especially if, for instance, you'll get a lot of online surveys, and that's voluntary. People have to volunteer to do these online surveys. And if that's the case, you have to misstate this. You cannot generalize past your sample. And that happens sometimes, and it sucks because obviously we always want to answer the question at the population level, but sometimes you can't. And a good statistician will be honest about this and will not lie and say that their study generalizes beyond, because there could be consequences to misidentifying your information that are quite serious actually, right? So we have to be honest about this. So somebody asked earlier if statistics is always numerical summary. And I said, a lot of times we are concerned of the sample. Somebody, I can't remember who, but somebody said that, is it true that statistics is always looking at numerical summary of your sample? And I said, yes, because statistics is a quantitative science basically, right? So, but a statistic needs to be separated from a parameter. Right, a parameter in general is a characteristic of the population, basically. Right, so I'm gonna say, and this characteristic can be numerical. Most of the time, it actually is. Right, so let me just kind of make this known that this is, this characteristic is often numerical. Right. Right, this is always a numerical value of the population. So a parameter does not describe the sample. It describes the population basically. Yeah, so the question is, if 75% of people of a certain population believe that global warming was affecting their daily lives, would that be a parameter? Yeah. So if I said that, and if I had data, if I had evidence that this is a true population parameter, so if I say something like 75% of the population believe in global warming, right, then that is a parameter because I've stated it at the population level. But if I say that 1,000 people from the American population was sampled, 75% of them said they believe in global warming, that is not a parameter, right? So if I'm speaking at the population level, that is a parameter. But if I'm speaking at the sample level, it is not a parameter, basically. Exactly. So that's exactly it, Emma. A statistic encompasses the sample's data, while a parameter encompasses the population data, right? So let's be clear here, basically. A statistic encompasses the sample data. A parameter is a population level numerical value, right? And to Melissa's point, the goal is to make inference at the population level, but let's be clear that any inference we're making is not a parameter, basically, because a lot of the times you do not know the parameter value. You want to make an inference with the population parameter, but you just don't know what it is in practice, right? So repeat this again. A statistic is actually something that is going to encompass the sample data, but a parameter itself is a population characteristic. The problem is that we do not have every unit of the population. And because of this, a lot of the times the actual true parameter value remains unknown, because we have to actually sample every person in the population to determine that parameter value. We do not have it. However, we can use this sample statistic to make predictions about the population parameter, right? So this is Melissa's point. So the goal of the actual thing is that, yes, you want to use the statistic to actually make an inference at the numerical value base. We just don't know what it is, right? So to answer your question about, so let me look at your exact question. You said, wouldn't the goal be to use, oh, I see what you're saying. So, oh, I see what you're saying. So Melissa's saying, why are you saying descriptive statistic? Isn't it inferential statistics? So I want to be clear here that the descriptive statistic is going to be used to make an inference, right? So this actually goes back to the point here where somebody said, I think it might have been you as Melissa, that said that isn't 85% here an inference, right? It is an inference but I had to complete it. So technically speaking, the estimate, I'm estimating that at the population level, right? This is an estimate. I'm saying that the sample population, 85% of them said yes. I'm going to use this descriptive statistics to go further and make inferences, basically. Oh, okay, like there's two Melissas. Okay. Yeah, so, but you guys asked a similar question, ironically. You have the same name. Because why is that? Because Melissa 1, right? Sorry, said that isn't 85% the inference? Is both the inference and the descriptive statistic. How come? Because Melissa 1 said that isn't this going to be used to make an inference? And I said yes, but it's not complete. I'm going to talk about the margin of error in the context of this inference. But then Melissa 2, right, said, isn't it an inferential statistics you want to use? And I'm going to say that the descriptive statistics you use, right, is going to be that you use to do a numerical summary is also the statistic you're going to use to make an inference, right? So you always first just illustrate your data, but then we're going to use that same statistic to make an inference, basically, later on. But when I make this inference, I'm going to talk about the margin of error, basically. Yes, a parameter is at the population level, right? But the statistic is at the sample level, basically, right? So we have to keep in our mind that a parameter is a characteristic of the population, basically. So a parameter is always going to be a numerical value. A parameter is a numerical value of the population, but we will use our sample data to make an inference to guess at the true value of the parameter. So I'm going to repeat this again. So the parameter is always going to be the population level. We don't know what it is because we cannot sample every member of the population, but we will use statistics to make an educated guess as to what that parameter value happens to be. So the statistic of the sample is always going to be used to estimate that parameter value, which we do not know what it is, basically. We will do statistics, again, to estimate, to guess what that parameter value happens to be. We just don't know what it is in practice. And that is the process of inferential. Exactly. That is the process, basically. When we start making guesses, educated guesses, that is the process of inferential statistics. Exactly. I think you had your hand up. Melissa, do you want to ask your question?
Oh, sorry, you just clarified that. Thank you.
Okay, cool. So yeah, that is exactly the process of inferential statistics. We want to guess at the parameter because we don't know what it is. We have to use statistics to do it. Right. So from the example above, we're going to guess exactly. We are always going to have a combination of both descriptive statistics and inferential statistics. Why is that? Because at first, before you can even make an inference, you need to describe your data. You need to first obtain that descriptive statistics before you make the inference. So every study will have a combination of those two things exactly. They'll always both feature in the study. It has to be that way. Right. So in the example above with the people who believe in heaven, of course, the descriptive statistics is 85% believed in heaven. We're going to use that eventually because as you guys noted, it's the process to make an inference of the population proportion who believe in heaven, because we don't know what it is. All we know is that among the sample, 85% believe, but we need to go further, and then we're going to use that statistic to make a guess at the population proportion who believe in heaven. Exactly. We don't know what the parameter value happens to be. We have to use statistics to estimate it. That's exactly the point. That's the entire point of the course, by the way. We have to use statistics to guess at the population proportion, the parameter. It's always going to be the case. But that's actually the whole point of statistics, by the way. We have to make an educated guess as to the parameter value. We don't know. We have to estimate it always using our data. That's actually the entire point of statistics, right? We're always guessing at the parameter value. We have to use statistics to do it. So someone said, cool. Okay. So let's look at an example here. For several years, the Gallup poll has asked, do you think abortion should be illegal under any circumstance? Legal under certain circumstances or illegal in all circumstances? The poll reported in May 2014, based on a sample of 1,228 adults, that the percentage of those three responses were 28%, 50%, and 21% respectively. Are these values of statistics or parameters, and why is that the case? What do you guys think? Is this statistics or parameters? Exactly. So this is a statistic because, as Emma said, it is based on the sample. And so we have to keep this in mind, right? It is not a parameter because we don't know what the parameter value happens to be. We have to use this statistic to estimate the parameter value. We just don't know what it is. But I want to point out that Gallup polls are polls on American adults, right? So the population is, we want to know what the American adult thinks about abortion, but we don't have their statistics. We don't have their parameter value. We have to use the statistics based on the sample of adult Americans that were sampled, and that was going to be, we're going to estimate that. Yeah, so Gallup poll, so I didn't specify it here, but Gallup polls is a poll in American adults, basically. So, Gallup polls, they're sampling American adults. So that's the subject, right? American adult is the subject, right? But I personally would be a bit more specific if I'm asked, this is a textbook question, but if I was going to, myself ask you guys a question in a quiz, I'd be more specific. Cool. And let's do a little bit more. So this is exercise 1.8. It says the current population survey is a monthly survey of households conducted by the U.S. Census Bureau. A CPS of 68,000 households in 2018 indicated that of those households, 9.6% of whites. So it should be American adult. Did I put Americans? Yeah, American adult. A subject is just an American adult, basically, right? But the set of all American adults is your population. Yeah. So a CPS of 68,000 households in 2013 indicated that of those households, 9.6% of whites, 27.9% of the Black people, and 23.5% of Hispanics, and 10.5% of Asians had an annual income below the poverty line. So the question is, are these numbers statistics or parameters? Explain. And then the second question, the follow-up, says that a method for this text predicts that the percentage of all Black households in the United States have an income below the poverty line is at least 25%, but no greater than 29%. What type of statistical method does this illustrate, descriptive or inferential? And then why? Exactly. So we have to be, this is still a statistic in the sense that there are more than 68,000 households in the United States. So we only sampled a fraction of them. And also it says a survey of households basically, right? So you didn't get everyone. But it is inferential statistics. Why is that? Because we are now saying that we estimated that it predicts, right, that among Black families, the poverty line is at least 25%, but no greater than 29. This is inference, basically. Yeah, this is a statistic because you haven't sampled everyone. You're taking a survey on a fraction of the population, and unless the actual survey sampled everyone, every member of the population, you generally don't have a parameter. You have a statistic. Unless your survey sampled everyone, which generally cannot, obviously, because then there'd be no need for statistics, right? Yeah, exactly. So as Emma's saying, there's a margin of error. Hey, you guys are figuring out early. There's a margin of error here, right? So you can see that it's saying that it's at least 25%, but no greater than 29%. That is a margin of error base. So this is actually the first demonstration of margin of error, right? This is a demonstration of margin of error. Margin of error. This is actually not quite the margin of error, but it is related to margin of error. So the margin of error is not 4%, but 4% is the interval. It's called a confidence interval. So it's a 4% confidence interval. Confidence interval, but I will say that, yeah, the margin of error is about 2%. Exactly. It's about 2% because the point estimate is 27.2, right? Your margin of now 27.2 is somewhere between 25% and 29, basically, right? So this is actually, so Emma, I think it was Emma's. It was not Emma's age, right? So, there was an understanding here that the point estimate is 27.2. Now it's literally 2% away from 25 and about 2% away from 29. So the margin of error is about 2%. But the confidence interval is 4%. This is the first demonstration of inferential statistics, right? So this is when you saw inference happening here. Let me see the questions here. So the margin of error refers to exactly, so you're really referring to how much your estimate varies, basically. So we really want the margin of error to be small because then we feel more confident in our estimate, basically, right? So this margin of error, you want it to be small, basically. This is actually not bad. 2% is not horrible, but it's not like great either. We can make it probably better, right? Do you figure out that proportion? Do you figure that out by comparing the proportion of Black people within the sample? So to figure out the actual, to figure out the proportion, what they probably did, Brianna, was they asked all the families what their actual household income was, and then if your income was above the poverty line, you got a value of like 0. If it was below the poverty line, you got a value of 1, right? So that's how they probably estimated it. So that means that there's an average poverty line in US, and then within each ratio group, they figured out how many families are above or below that line. And if you're above that line, you got a value of 1. If you're below that line, you got a value of 0, and that's how they found the proportions, basically. Yeah. So in this example here, a subject is actually the households themselves, basically, not the people. So actually, this is a good question. Oh, sorry. Confidence. This is confidence. I'm so sorry. I'll write that again. This is a confidence. Yeah, I'm so sorry. Let me write that again. I just want to point out that was a good question somebody asked about what the subjects are. It is not people in this example here. It is actually households, basically. Because this is a good example of how here an example where it's not true. The subjects are actually they're not people here. They're households. So I just want to reiterate this. I mean, this is a subjects. Right. So we need to. It's not. Yeah. It's one household exactly. One household. So I'm glad somebody asked that question. So here it's actually one household, not people. Right, so it doesn't always have to be people, and we have to recognize when this distinction happens, basically. Oh, you don't need to know that just yet, too, man. That was just me. You don't need to know that just yet. That's a to be continued. So don't worry about confidence intervals just yet. That's gonna be confusing until we talk about don't worry about that just now. In fact, you won't see me talk about confidence intervals at all for a couple of weeks. That's not. Yeah, don't worry about that for now. that's not, we haven't gotten that part of the course. That's towards the end of the course. It won't make sense just yet until I first define a couple other concepts before it. No, definitely not. So margin of error is not on the quiz. The only reason why I brought it up here is because someone else mentioned it beforehand. So we are not going to talk about confidence intervals or margins of errors for a little while. Yeah, those are, so don't worry about that. But these are parameters though. Yes, these are parameters. Sorry, these are not parameters, these are statistics because they're characterizing the actual sample. We do not know what the parameter value happens to be. These are not parameters because we don't have the actual full population. What we have here are actual sample statistics. These are not parameters. But don't worry about confidence intervals and margin of errors. That's way above. We are way ahead of this. That's not even on the quiz. This is not going to be discussed until probably like week 7 or 8. This is way ahead, basically. Don't worry about these concepts just yet. But to clarify your question, Boz, right? How do you say your name? Is it Boaz or Boz? But yeah, this is not a parameter because these are numerical values of your data, right? So we only sampled 68,000 households. That's not a parameter. Cool. So this means that somebody asked, isn't it true that in your summary, you're always looking at like a combination of descriptive and inferential statistics? And I said, yes, right? So in general, the field of statistics concerns itself with both of those things, and every study will encompass both of those things, right? So statistics will always encompass these 4 things: study design, but this is really epidemiologists concern them, right? Epidemiologists. Right? Because the study design itself will obviously determine the data you actually get. This is really, when you want to collect data, you have to concern yourself with the study design, because sometimes the questions you want to address, it depends on the data you actually get. But we as statisticians, or me, really concern ourselves, right, with these 3 things here, right? So the first line of defense is always to illustrate your data, as someone said, and then in that same process, we're going to use the descriptive statistics we actually get to make inferences about the population level, right? Now, of course, in doing this part here, which is perhaps the most important part of statistics, the inference, you have to be sure that we have a representative sample. So we're always going to ask ourselves what our sample looks like before we even do the inference, because your inference can be very wrong if your sample is not representative, basically. And this is actually why in this course, I'm first going to talk about this before I talk about the inference, because there's no point in talking about this if your sample doesn't make sense, right? So before you even talk about inference, you need to know if your sample is even representative, and if it's not, you can't even really do part 3. Right? So this is the most important part, but it doesn't really make sense if this is not representative. So this is why in this course, we start with defining what it means to be representative before we even talk about inference. This is why inference actually happens in the second half of the course, before we get in our mind what it means to be a representative sample. Okay, so I'm going to first describe variables, because a lot of the actual numerical values we get are going to be on variables themselves, right? So I'm going to first define them. And actually your data is a collection of variables, basically, right? So data is literally a collection of variables, and that's what we're going to define them first. And actually, by the way, your self-reflect, I don't know if any of you saw the instructions for the self-reflect, but it's going to encompass this part here. So if you're at all confused, let me know, right? So data is a collection of variables, right? So let me just write that now. Data is a collection of variables. Right, and that's what we need to know. We need to define this, right? And I will say that this is actually on your quiz as well as your self-reflect. So if at any point you're confused, let me know, and we could go over it. And then randomization is the process in which you get a representative sample, right, to obtain representative sample. Right? And that's how we're going to concern ourselves with these 2 things. Okay. So what is a variable? It's a measurable characteristic. Right. So for instance, an obvious example of like a variable would be something like your political affiliation, Are you a Democrat, Republican, Independent, right? That is, so that's to be continued tomorrow. So I'm going to discuss that in a little bit, a couple of slides. I haven't quite explained what it means for representative just yet. That'll be in a couple of slides. So that's actually that is really quite an important topic. So I'm going to spend a couple of slides on it. No, I haven't described it just yet. That I have to take a bit of time to kind of elucidate for you guys. Okay, so a variable is a measurement, as a measurable characteristic. So for instance, your political party, if you're a Democrat, Republican, Independent, that is a measurable characteristic that is going to vary across different subjects. So if, for instance, my subject is, let's say, you know, an individual person, then your political affiliation is going to vary across each person, right? Somebody may identify as like a Democrat, another person may identify as an independent, and somebody else may identify as a Republican, right? So these are different identifications that are varying across each person, right? And so that's in some sense way you can control the change of those measured characteristics across a subject you're looking at, right? So this example here, the subject is people, right? And you can see that what is varying across each person is a different ID, right? So because no two people are the exact same. So ID number is going to change across each person, but in addition to ID changing, their opinion on abortion is going to change, right? Opinion is yes or no. This is variable one. Your opinion is variable one. It's going to be yes or no. It's a thing that is changing. It's varying across each individual. So this idea of varying is important, right? Your political party is also going to vary across the subject. So does your gender. Now this already is a very archaic system, right? Because I think this book is actually at least 7 years old. Because now it really only, most examples will say gender is male or female, right? So I apologize, right, for that. It's a really kind of outdated book, right? And then employment, yes or no, right? So these are all different characteristics going to vary across the subject. And in this example here, the subject is people. So that you cannot, for instance, have two people with the same ID, right? This is how, and you can see this is how data always looks. It always looks like, right, different, so I didn't mean to that. It looks like different variables, right? Yeah, so actually here there are 4 variables. Yeah, here we concern ourselves primarily with 4 variables. I mean, you could look at ID as a variable, right? But the ones we concern ourselves with are really actually these 4 here, right? You could look at ID as a variable as well, in the sense of like ID is changing across each person, because obviously ID 1 has a name basically, right? So person ID 1 has a name, but you don't know what it is. Person 2 has a name. So really there's actually 5 variables because you gave each person a different ID number, but you really only concern yourself with the 4 variables here when you want to do any kind of statistics on it. But to be clear, ID is a variable as well, because your name is not ID 1 basically, right? Your name is something else, but you were given a label of 1 basically. Right, so technically speaking, there are 5 variables. So we really concern ourselves with the 4 variables that we could do any kind of inferences on, although ID itself is also a variable because somebody was given an ID of 1 or an ID of 2 all the way to n. Does anyone know why we give people, yeah, you would ignore ID when you do the data analysis. Does anyone know why we give people ID numbers instead of using their names? We wouldn't use it in the analysis, Samara is saying, but does anyone know why we actually, exactly, anonymity basically. So they feel anonymous, exactly it, right? So we don't want to release data that actually shows people's identifying information, right? Because that's inappropriate, right? So we don't want to have identifying information, right? And that's an important thing, right? So this is exactly why, in some sense, this is in some sense why we have IDs, even though exactly confidentiality issues. So we have to be a bit careful here, right? So we don't want to, especially because I, as a statistician, will get this data that is a secondary source, and I shouldn't be able to know who said what, which person had what opinion. That would be a breach of confidentiality, which is why we give them ID numbers. But to be clear, this is not going to be used in the analysis because it doesn't make any sense. It doesn't really serve any purpose other than to label different people with different ID numbers, but it doesn't give us any information. Okay, so let's look at variables and their measurements, right? So a variable is countable when we can count out the set of possible outcomes. That seems kind of circular, right? Because like in the definition of countability is count, right? But it's really not that. Yeah, the idea is like a subname, Curtis. Exactly. Yep. So it's kind of, it seems a bit circular to say countable is when you can count out the outcomes. And when I first the definition, I kind of laughed basically because it almost seems circular, like you're using the thing you want to define with the name itself, but it's not really that trivial because, for instance, it's not always the case that you can list out all the possible outcomes, right? So for instance, height. Your height can really be any number between 0 to infinity, and you cannot count them out. How come? Because you could be, for instance, 60 inches, right? Or you could be 60.1 inches, 60.111, 60.1112. You can see that it is exactly the same as discrete and continuous. It's exactly it, right? Because you cannot, if you have too many, if you, for instance, have a continuous outcome, you cannot count out all the possible outcomes. As I did with height, you can take any value between 0 to infinity when you list out height. It's not a countable outcome, basically. But when you can count out a discrete process is really when you can count out the possible outcomes in, right? So for instance, when you roll a fair die, there's only 6 possible outcomes, right? You can, it's either 1, 2, 3, 4, and 5, or 6. Not only is this actually countable, it's actually finite too. Every finite outcome is countable, right? That's something to point out, because if there's an end to the possible set of outcomes, it's obviously going to be very countable, basically. But not all countable outcomes are finite, right? But they should always be discrete, as was pointed out. How do you say your name? If you can either just because I like to kind of know who I'm speaking to. Okay, Abdi, cool. Yeah, this is countable, Emma. Okay, so as Abdi was saying, yeah, when you have a discrete process, so finite means that this is finite. So a finite means, for instance, that there's an end to the output. A finite means that so finite equals there's an end to the possible outcomes, endpoint to possible outcomes, basically, right? So this is actually finite because there's only 6 possible outcomes. What is also finite, as someone said, the abortion opinion, right? So opinion yes or no, there's only 2 possible outcomes. Now this is finite, which means that it's countable actually, right? You can count, there's only 2 possible outcomes, yes or no, and there's no more than that basically, right? So every uncountable outcome, like Abdi said, is actually continuous, right? Like you cannot list out all the possible outcomes, basically. There are infinitely many of them, which means that, like, for instance, with height, are you 60 inches or 60.1 or 60.12, 60.13? You can see that it keeps going. You cannot actually count out all the possible outcomes. You cannot list them out because you have to consider even the decimal place, infinitely many decimal places after 0. But you can see that decimals don't actually end. And because the decimals don't end, you essentially have infinitely many values the outcome could take. This is uncountable, right? So this is important to know because the actual statistics we can do on uncountable versus countable outcomes are different, right? Exactly. So as said, a countable outcome is when you can count out the possible set of outcomes, but when you cannot count it out, it becomes uncountable, basically. So the number of children is so the number of households, the family household number. Yes, if your subjects are family households, and your question is number of children, that is a countable outcome, basically. Usually you have a finite number of children. That is a countable outcome, basically. If, for instance, my grandmother had 16 kids, which is on the higher end, obviously. But actually, that's still a finite number of children you can have. That's a countable outcome. Okay. So I'm actually glad that Abdi brought up the notion of discrete. The size of the universe would not be finite. Yeah, the size of the you have good examples. Yeah, the size of the universe is definitely not finite because the measurement will actually change, but it will just by vastness alone. This is infinite, basically, right? But yeah, the size of the universe is definitely not finite. The vastness alone makes it infinite, basically. Earth is it depends on how you define Earth, basically, right? It's whether or not it's a finite process. Even if you talk about Earth as a landmass, the actual measurement of the measurement itself of Earth is still infinite, basically. But if you talk about one planet Earth, or if you're talking about the number of planets, or the fact that planet Earth, there's only one planet Earth, and that's finite. It depends on how you define the measurement, basically. So a variable is discrete. Yeah, so that's why I'm glad that Abdi brought up the notion of like continuous versus discrete. A discrete variable is one that is countable. Discrete and countable are used interchangeably. Why is that? Because every discrete variable has a countable number of outcomes, basically, right? So these are, in some sense, synonymous because obviously a discrete variable is one that is countable, basically. In some sense, they're interchangeable in that way, basically, right? Whereas continuous variables are one where the outcomes are uncountable, basically. So in some sense, they're interchangeable, which is why I'm glad it was brought up early. Right? Yeah, discrete is always countable, basically, whereas continuous is always uncountable, basically. They're interchangeable in that way, right? So number of siblings, for instance, and someone brought up the family household is of course going to be countable. It's a discrete variable, basically. It's discrete, right? Because the outcome is of course countable, it is discrete, right? So we are using countable versus uncountable to define. We're going to stick to these two definitions, but technically speaking, our lecture should take a break, right? But the reason why I didn't say is we got a little behind, but technically speaking, we should have a break in between. Our lecture shouldn't have continuity in general. At least there should be a boundary point between the two different hours in our lecture, basically. Generally, in theory, I should have a break at like 1 o'clock. Yeah, I should have a break at 1 o'clock. But today we're gonna have a continuity because we're behind. I'm sorry, guys. But in general, there should be a boundary point between our lectures. It's gonna be an infinite lecture today, guys, because yeah. It was, oh my God, it was not a discrete comment. No, apparently I should have had a break at some point. Sorry, guys. It was not a discrete, not a subtle comment there. But hey, that's statistics in action, so I can't get mad, basically. That's funny. But yeah, you can all look forward to a finite lecture next week, basically. Well, the lecture is always finite, basically, because you see, we always have an ending point. But there will be definitely a finite, there'll be separation between our lectures next week. Thank you for that joke. It was a good use of statistics, but I can't get mad. So people who are watching the lecture will have a good chuckle because we'll really have the distinction between discrete and finite, at least, or discrete and continuous. Okay, so in practice, guys, we will have some discreteness or there's some separation in our lectures, but today is going to be continuous because I kind of fumbled the ball a bit and got behind. Sorry, guys. But yeah, so number of siblings is discrete, but gender itself is also discrete because there's, a finite number of categories. But I do want to point out that the reason why I kind of put these two examples is because there's something different about them. Right? Well, does anyone know what the difference between these two different discrete variables are? Like there's something intuitively different between these two things. Does anyone know what it is? They're not the same type of discrete. So one has what the other one does not have. There's something that the first one has, the other one does not have. Does anyone know what that is? An order, exactly. The first one has an order. Hey, you guys are getting ahead, basically. I'm going to definitely define categorical, exactly. So because gender is qualitative or categorical, as you guys are seeing, there is no order to this one. They're both discrete, but this one is inherently different. There's no order, right? Whereas this one has an implicit order. So we have to keep in our mind that not all discrete variables are going to be quantitative, right? Not all discrete variables are going to be quantitative. There's something inherently, exactly, there's going to be an order. We're going to call ordinal variables, right? So ordinal and nominal are going to be the terms. Interval is something else. Interval is going to correspond to the continuous variables, basically, right? So the ones that are continuous are always going to be interval, right? Now, the one, and actually not quite ordinal. So that's a to be continued. So we are going to talk about nominal, ordinal, and interval, but you're going to see nominal and ordinal in the context of like qualitative variables, but the ones that are numerical are always going to be interval, basically. But these are three things we're going to talk about: is ordinal, interval, and nominal. Okay, so this one has no order, as you guys are determining, whereas the first one does have order. Okay, so now let's think about this. A variable is continuous if it is uncountable. So examples like weight, height, age, and years, because our age is always changing every second, right? We're always getting a little bit older. Our height is, in fact, changes throughout the day. If you measure yourself in the morning, you will shrink by the afternoon, right? Because when you're tallest you ever will be when you first wake up, right? And then when your vertebrae kind of collapses a bit, when you walk, you get shorter in the day, right? And the weight is always changing as well. There's body fluctuations even within the day. The lightest you will ever be in a day when you don't eat. The minute you put water in your body, your weight is changing right away, right? So yeah, pandemic weight too, yeah. we can't consider our regular weight as the pandemic weight does not count as a regular weight. We have to get some freebies there, right? So there's that too. Quarantine 15, yeah. Instead of freshman 15, you all got quarantine 15 basically. Saxy said it at 5'2". So I said it in the morning, I said it at like probably 5'7". And then by the end of the day, I get to 5'6.5", basically. Oh no. So I'm actually tall, right? So to me, this is like foreign thing to me. So continuous and discrete are both types of statistics, but they're just not the same. They're not the same type of variable, basically. They're all statistics of some sort. You're just not the same type of variables. There can be different variables. Okay. Cool. If you put the ages in a range, yeah, that's a good question. So somebody asked, what if you put the ages in the range? You can do that too. You can discretize age. So for instance, if you have something like, less than 18 to, let's say, 25 to 40, etc. This is just discretizing, basically. This is discretizing age into bins. But in general, your age is always changing. So for instance, when you have a birthday, you're exactly, let's say, n number of years old. The next day, you're n number 0.1. In fact, it's changing every second, right? So it could be, for instance, 18 and a half, then you're 18.75, and your age doesn't sit it doesn't sit in a continuous scale. It's not constantly the same age. Your age changes every second basis. So for instance, you're 18 years old exactly as your birthday hits, and exactly the minute you were born. If you're born, let's say 6:00 a.m., then you're 18 at exactly 6 a.m. But when the day progresses, you're 18.1 or something, because time is a continuous variable, basically, right? That's why your age is never the same, right? Even in the day of your birthday, you're not exactly that age during the day. Your age changes every hour, basically, right? Because you're technically speaking, you're 18 or you're 19 at exactly that moment you were born. Then your age changes every minute, or every second, actually. Discrete variables do change, but they change in known bins, basically. So for instance, if you have 0 siblings, you're an only child, the minute you have another sibling, you're changed by a value of 1. Then you have another sibling, you change again by a value of 1. So there's discrete bins, and there's no values in between those bins. So for instance, you cannot be like person and a half. So even though you're seeing a change, it's a change in a very obvious bins, basically, right? So go from 0 siblings to 1, you go from 1 sibling to 2 to 3, and you cannot go, there's no values in between those bins, basically. That's what it means by discrete. It changes, but in a very obvious and known way, basically. Okay, so I do want to point out that we had discrete versus continuous variables, and every discrete variable is one that has a countable outcome. The continuous variables are ones that have uncountable outcomes, right? But a quantitative variable is any variable that has numerical values as its scale base. What does that mean? It means that a quantitative should not be confused with continuous. It's not quite the same. Now, all continuous variables are quantitative, but the converse is not true. I'm just going to repeat it again. So, continuous does imply quantitative. It has numerical value at a scale, but quantitative does not imply continuous. But it's not true that this implies continuous. Why is that? Because discrete outcomes that are quantitative could actually be themselves. You could have discrete outcomes that are quantitative, right? So for instance, number of siblings is a discrete outcome, but it has numerical values. So that is quantitative basically, right? So every continuous outcome is quantitative, but the converse is certainly not true. So we have to keep this in mind, right? So annual income, annual income is another one where you could put into bins, right? So it could be you could put it into bins like you make less than 50,000, you make between 50,000 to 100,000, etc., or it could be continuous, right? Yeah. So if I ask you is a variable, let's say quantitative or discrete, quantitative or let's say qualitative, then you should make a note that since the outcomes are numerical, it is going to be quantitative, right? So it depends on what I ask. If I ask something like, is it quantitative or qualitative? You should know that, well, the scale is numerical. So even if it's discrete, it's going to be quantitative. Then if I ask something like, is it nominal or ordinal? Then I'm only asking about the qualitative variables. That's a different question entirely. So it depends on how I ask the question. But if I ask it in terms of like quantitative or like, let's say qualitative, then you should know that even if it's discrete, but you have a countable number of outcomes that you can list out in an order, that is still actually going to be a quantitative basically, right? So for example, annual income, if I make it into continuous scale in dollars, like let's say in dollars, and this is going to be continuous, but it's quantitative. But number of siblings is going to be something like, quantitative but discrete. And the other two are going to be, of course, quantitative and continuous. Actually, this one depends on how you list it basically, right? So if you list it in terms of like actual years, then it's going to be continuous. But if you talk about like how many levels you completed, so in years or levels, they're both quantitative, but not the same, right? So in years it's going to be discrete. It's going to be continuous. But if I talk about levels, like you went through like grade 1, grade 2, then it's going to be obviously discrete. So it depends on how you list it. If I talk about annual income in terms of how much you make in general, there is really no limit to how much you can make. And you can make, for instance, $130,000 0.1, $130,000.2. But if I ask you in terms of discrete categories, like you make between 0 to 50,000, 50,000 to 100,000, then it's going to be qualitative. It depends on how you actually express income. You can put it in bins, and if you put it in bins, it's going to be discrete, or you could put it in terms of like just dollars, where you don't have a bins basically. So it depends on how I define it. So continuous implies quantitative. So for instance, age in years is a continuous variable that is obviously quantitative because the scale is numerical. But the converse is not true, because here's an example. Here's a quantitative variable, which is number of siblings, but it is not continuous because you cannot be 0.5. You cannot be a sibling and a half. You cannot have a sibling and a half. You cannot have 2 siblings and a half, basically. So because your siblings can only increase by a value of 1, this is quantitative because it's numerical value, but it is not continuous because it doesn't have infinitely many outcomes, right? It has like discrete outcomes. That's why That is why quantitative does not imply continuous, because number of siblings is not continuous, but every continuous outcome, be it age and years, like your weight, your height, is always going to be quantitative because it's numerical value. Yeah. So we have to keep in the distinction between quantitative and continuous is that a quantitative variable can be discrete, but obviously that because it can be discrete, which is not continuous, you do not get quantitative implies continuous always, but continuous is always quantitative. Right. So we also have a variable that is categorical when the scale of measurement differs in quality, but not numerical values, right? So this means that like there is no order. Well, there could be order, but it is not numerical, right? It is always not number of siblings to be continuous. Yes, exactly. Number of siblings is an example where you have that quantitative does not imply continuity, so we cannot map that on basically, because it can be the number of siblings is clearly discrete, right? Yeah, so continuous implies quantitative, exactly, because every outcome on a continuous scale is numerical, but you cannot say that quantitative implies continuous because number of siblings cannot be anything between a boundary of like 0, 1, 2, etc. Exactly. So Emma's got a good example where you can see directly how it's working, right? So we have to keep in mind that sometimes a quantitative outcome can be discrete, and we have to have this in our minds, basically. Okay, so a variable is categorical, right, when the measurement scale differs in quality, but your outcomes are not actually themselves numerical, right? So gender is an example where you don't have a numerical outcome, but you can see clear different categories, basically, right? So when you have different categories, but it is not numerical, this is a categorical variable, right? So for instance, opinion on abortion, basically, I'll add this here, right? Because that was our very first example. So legalization of abortion, right? This is abortion. This is yes, no, right? This is differing in quality because you cannot say yes and no at the same time, but there is no numerical order here, right? So, and there's no numerical value, right? So marital status, you're single, married, divorced, widowed. This is obviously different categories, but you cannot be in all of them. So it's differing quality. Same with favorite color. Actually, one semester, somebody said that favorite color is a weird example because if you put color on a gradient scale, it looks continuous, right? So because even red can be expressed in terms of hue, and that's continuous. But let's pretend we're looking at the colors themselves, not the hue scale, right? Then it's obviously going to be different categorical categories, right? All of the variables in slide 19. So this is actually this one's here. These are all examples of categorical variables because you can see that there's no actual numerical values. There's no numerical outcome, right? So when you ask them, when you take a measurement on, for instance, political party, you're either a Democrat, Republican, or independent, but there's no numerical value there, right? The same with gender, employment, opinion. These are all, right, categorical because you can see that the quality of the response is different. It's not the same response in each category, but there's no actual numerical thing there. But I will say that one thing you note about this is these variables are what? Are they discrete or continuous? These are all discrete. So I will say that every categorical variable is discrete. They're all discrete. So while it's possible that quantitative variables can be continuous or discrete, all categorical variables are qualitative. Yeah, so qualitative and categorical, yeah, those are synonymous, Brianna. So categorical and qualitative are synonymous, exactly. It means that all outcomes are discrete and all outcomes have no numerical value. So there is no numerical value, but they're all discrete, right? In contrast, quantitative implies numerical value and they can be continuous or discrete, right? So all categorical variables are qualitative, which means that there is no numerical value, but some quantitative variables are discrete, some are continuous, right? That's a good question. So you're getting to my next point here, which is very, so you have a lot of good questions. That's an important one. So what happens when you intuitively notice order in your qualitative variable? So it is entirely possible that you notice that your qualitative variable has some order. It is still qualitative, but these are special variables. Why is that? Because they can be translated to quantitative discrete variables. So that's a good question that was asked. What happened, right, when you notice that your variables are like never, or for instance, you meant never, mild, or severe, where you can see there's a gradient of increasing severity. And so you cannot say you don't notice order there. You definitely notice order. How do you address that? They're still qualitative, but you can see that there's a way to translate them to quantitative variables, which is what you did, right? So never goes to 0, mild goes to 1, severe goes to 2. In a natural form, it is still qualitative, but you translated it to something that is quantitative in a second, and when you say 0, 1, 2. And by the way, that actually makes those variables ordinal, right? So this is all categorical variables are discrete, but whether or not they become ordinal or nominal is when you can determine order in a way that H did, right? H, you'll have to email me. I keep forgetting your name, and I want to make sure I know because you ask a lot of questions. You give a lot of insights. Send me an email so I don't forget. So when I'm looking at your name on Quarkus, I can see it. Okay, so that's a good question that was asked, and we should have it in our minds that some variables feel intuitively ordinal. There's an order to it, and you have to recognize when this happens, basically. So I just want to point out, and before I answer the questions, that was a very clever question, because sometimes you notice that these qualitative variables have order. I will comment that number of siblings is both quantitative and discrete. Some quantitative variables are continuous and some are discrete, but all categorical variables are discrete. So this is a good summary page for your quiz next week. This is right there. All of these variables are discrete, but some of these ones are discrete and some are continuous. Yeah, so some quantitative variables are continuous and some are discrete, but all categorical variables are discrete. So whenever you have a variable that is categorical, they're all discrete. But when you have a quantitative variable that is numerical in value, some are continuous and some are discrete. Now, the scales of measurement is what some of you actually noticed ahead of time when you said that, when you mentioned nominal, ordinal, or interval. And I do want to point out that whenever you have, the reason we need to have a distinction between quantitative and qualitative is because whenever you have a quantitative variable, be it that it is discrete or continuous, because it is numerical, the scale of measurement is always interval, basically, because you can compute differences, basically, right? So even if your variable is discrete, it is still interval in the scale of measurement if it's numerical, because you can compute differences, basically. Whereas you cannot talk about differences with categorical variables, basically, because you cannot take differences of non-numerical values, right? So whenever you have a quantitative variable, you can talk about interval scales, basically, right? When it's possible to talk about differences between the values, you have intervals. So for instance, Sarah has 3 sisters, right? And Cindy has 2 sisters. What is the difference in the number of sisters that Cindy and Sarah has? Now you can say 1 because 3 minus 2 is 1, basically. So now you have an interval scale when you have this ability to do differences, basically. This is exclusive to any quantitative variable, be it continuous or discrete, right? You cannot talk about this interval scale of measurement when you are talking about, right, categorical things. So some more examples could be like the difference between making $40,000 and $300,000 is $10,000. You cannot talk about this in terms of categorical variables because you don't have this intervals thing. Or for instance, saying that John is 10 years older than his brother is another way of, right, talking about something that is actually quantitative, because years is quantitative and continuous. You could talk about this difference, right? In contrast, whenever you notice that your scale of, whenever you notice you have a categorical variable, you either have nominal variables or ordinal, right? So when you determine your variables are categorical, you automatically know you don't have numerical values or outcomes, but you then have to ask yourself whether or not you notice order or not, as H said, right? So whenever you notice order, you're not in this scenario here. So you are not nominal if you can notice order. But when your variable has no inherent order, you have a nominal variable, right? Exactly. Whenever you don't have any order, you're at nominal variable. So whenever you notice order, you have to ask yourself, is it nominal or ordinal, right? So when you determine you're in categorical variables here, the question is whether or not you can determine order, right? If you determine order, then dismiss this here. But if you do not have order, then you are in the nominal situation here. There is no discernible order. So for instance, gender, and I again apologize for the fact that there's only a two-tier system here, or employment status, yes or no. And this is very nominal because you don't notice order in these outcomes, right? But to the example H gave with, never mild or severe, there is something implicitly ordered there, basically, right? And a similar example would be like something like, this is kind of similar to H's example where you have poor, moderate, good. There is something ordered here because poor is worse than moderate, which is worse than good. Now we can obviously notice this implicit order here. And if we wanted, so the variables you can actually translate, right, those to quantitative outcomes are the ones that are ordinal. Like you can notice a natural ordering in your variables and that cannot be dismissed, right? So for instance, social class, upper, middle, lower is like almost in the opposite. It's like in descending order here. This is descending because upper class makes more than middle class, which is more than lower class, right? So there is a natural order in these two examples here because you can place them in an order of like highest to lowest, or in this case here, highest, lowest, or lowest to highest. It could be, exactly, it could be increasing or decreasing, but whenever you notice an order, this is intuitively ordinal, basically. Whenever you can notice an ascending or descending order, that is certainly ordinal. Right? Yeah. So another example of like, let's say this would be like, belief in heaven, basically. Believe in heaven. Oh, let me not use lesson note. Let me use something like what? Let me use something where it's not yes or no. Something like, oh yeah, here's school, subject in school. Or let's say department is school department. Right? Where you're like, maybe life science, social science, computer mathematical science, etc. This is life science, social science, computer mathematical science. I'm the third one. Whenever you have different bins where there's no actual order, that's nominal. So your discipline, are you in social science? Are you in life science, computer mathematical sciences? That's also like nominal. Yeah, so Melissa's saying, isn't it, so there's already a natural order in quantitative variables, but the reason why it's not ordinal is because it's already numerical value, and therefore you already have interval scale. Because it's already numerical, the way you actually measure you can measure differences. Whereas even though poor, moderate, and good is actually ordered too, you cannot take a difference. There's no difference between poor and moderate. Like, how do you subtract poor from moderate? You cannot subtract them until you translate them to numerical values. So the only way I cannot talk about differences in here. This is why, even though it's ordered, you cannot talk about differences. Another good example is like, yeah, as Emma's saying, grades, right? Now, in your GPA, you get what? You get a GPA in terms of like something between 0 to 4. You also get a letter grade, basically, something between F to like A+. Now, I cannot take a difference between an F and a C because they're qualitative. There is no way to take a difference between an F and a C, but I can translate an F to a 0 on the 4.0 scale, and I can translate a C to a 2, and 2 minus 0 is 2. So what is special about the ordinal variables is that you can translate them to quantitative variables and then take a difference, basically. So for ordinal variables, they are not numerical. They are not numerical. They are still categorical. They are still themselves ordinal. You cannot call them interval. The only way this becomes interval is if I translate. So if I translate this to 0, if I for instance take this to 0, I take this to 1, I take this to 2, now this is quantitative. This is qualitative though. So while I cannot talk about interval scale in this original form, once I translate it to this, then it becomes interval basically. You have to translate them basically. Exactly. You have to, now the thing that is special about the ordinal variables is you can translate them basically. The fact that you can translate them into quantitative things makes them different from the nominal scale. But in the actual form here, it is still categorical until you make the translation. But the fact that you can translate them because there's a natural order makes them different from nominal variables, basically, because you cannot translate them to numerical things. Right? This is a distinction between those two different categorical variables. But to be clear, even if you notice this order, if you don't translate them, they are still categorical. You still cannot talk about differences until you make this transformation, basically. But if you look at your GPA, for instance, that's what they did, by the way. Whenever you give the department a letter grade, like you got an A, B, C, they translate your qualitative, they translate your quantitative variable, or they translate your qualitative variables here into something that is actually quantitative. So how do they do that? Well, if you think about it, if you got an A, right? If you got it like an A plus, A, A minus, all the way to an F. Well, this is a 4.0. This is a 3.7. This is a 0. So you see, they translated your letter grades. These are themselves actually, right? Ordinal. So this is actually ordinal. And this is actually interval, basically. Only after they've translated your qualitative variables is something that is quantitative can you talk about your actual overall sessional GPA or your cumulative GPA, right? So the transformation happens here, and then suddenly you see your actual letter grades translated into your GPA scale, where they translated your ordinal variables into something that is actually interval, basically. That's how they're doing it, right? So the first they need to make the transformation from qualitative to quantitative, and then they can compute your sessional GPA. Yeah, a natural order can happen, and it can happen with both numerical values or non-numerical values. Whenever you have an ascension or descension, that's an order. It can happen with both numerical or non-numerical values, but a natural order insinuates that you can actually feel an ascension or descension, basically. Right? So that's the thing here. Are you referring to this H? So Alva, when I say a natural order, I mean that like you can actually notice a descension or an ascension, and this can happen with numerical values or non-numerical values. It just means that you can order up your outcomes in a logical way, basically. But yeah, that's how your GPA is actually computed, by the way. Right. So for instance, your course grades, you've got an A, B, C, D, right, or an F. These are ordinal. How come? Well, because, right, there obviously an A is better than a B, which is better than a C, and etc. But I cannot talk about difference between an A and a B until I compute them into quantitative variables, basically. So an A goes to a 4, a B goes to a 3, and now suddenly I can compute GPAs, basically, because you can talk about interval scale with grades, basically, with numerical values. Whereas I cannot talk about interval scale with letters because they're obviously ordinal. I can talk about obviously interval scale with these numerical values. The transformation is interval, but the original letters themselves are not actually interval, they're still ordinal. Right? So that's something to keep in mind. So I don't think I have time to talk about this, but I will start at least with let's see. This is gonna be quite the big thing. Let me see. I don't think I'll have time to talk about this, but I will say that at least I'll start talking about it a bit. So I will say that I did say, and I did say, I think it was Samara that asked, I did say I was an IOU, it's what it means to be a representative sample. But I will say the first step towards a representative sample, right, is what? It is randomization. What does it mean to be a random sample? Randomization is a situation or a circumstance, right, where you ensure that everyone has equal chance of being selected, basically, right? So in inference, we really only know if so how do we know if our actual estimate is good or accurate? It's only good if our sample statistic is representative, right? So that means that we didn't do inferences on the sample that is not reflective of your demographic, right? So if it does not reflect your demographic, then it's not a good sample, right? So randomization is the method in which we achieve this representative sample. What does it mean to be random? It means that anyone has, it's truly a random process. Anyone has equal chance of being selected, right? It's a random process. That's what it means, right? So it means that you didn't favor one person in being selected in your sample than another person, basically, right? So it ensures your sample is unbiased. A biased sample is one in which you suspect that certain members are more likely to be in your sample than another, basically. That is not an unbiased sample, basically. So I will say that the first step, the most common form of randomization is called a simple random sample, right? So if you have a population of size big N and you have a sample size little n, a simple random sample is one in which, right, any sample of size little n has the same chance of being selected. So what do I mean by that? I mean that, like, if you have a big sample of size n and you want to draw a sample of size little n, any particular member of the population has a chance of being selected. There's no chance of one pocket of people being selected over another one. And then with this way, if everyone has the same chance of being selected, then you won't have a sample in which, right, you have certain samples that are more likely to be seen than others. So for instance, if I want to select, for instance, the height of typical Ontarian person in Ontario, basically the typical adult in Ontario, right? Then I would not choose, for instance, a sample in which college-age students are more likely to be selected in the sample than right, people who are like middle-aged or whatnot, or senior, because in this way, the sample is not representative, right? So you would not want one demographic to be more likely to be selected than another. So you have to sample in a way that you target every member of the population, basically, right? So this means every possible sample that you can generate has to have the same chance of occurrence, basically, right? So for instance, if I have a class size 60, and it's not true because it's like something around 200 people in the class, and if I assign everyone a value of like 1 to, let's say, 60, right, then I should, in some sense, be able to generate every possible sample of size n from this list of 1 to 60. Right? What do I mean by that? It means that if my sample, for instance, is, let's say, 2 people, let's suppose I want to take a sample of size 2 out of a sample of, let's say, 60 people, then it means that, like, if sample 1 is like, let's say, person 1 and person 30, right? Then sample 2, that consists of, let's say, sample 3 and 6, should be equally likely as sample 1 and 30. And I could take another sample, let's say, person 4 and 20, but no one sample should be more likely than the other sample to be found in the should be selected. So I shouldn't be able to select person 3 and 6 more often than person 1 and 30, 4 and 20, and et cetera, basically. Yeah, so I'm only going to test based on where I finished in the lecture, basically, right? But to be clear, if you think about every possible sample of size 2 you could generate, I should not be able to generate a person, let's say 3 and 6, more than I generate another person of 1 and 30, 4 and 20, and et cetera, right? So whenever you have a bias in your sample where you're selecting a particular sample size n more than another, this is a bias in some sense. So you don't want, exactly, you put numbers in a hat and you pick, well, you should not be able to pick a particular sample more than the other if you sampled randomly, right? So they should have equal chance of being selected. You shouldn't cheat in a way that, right, you selected one sample more than another, because you exactly, a lucky draw is kind of random. But if your lucky draw is not very random, then you have a biased sample, basically. So this is regardless of whether or not you have discrete variables or not. This is a different process entirely, Melissa. So this is referring to how you sample, not your variables themselves. Basically, every variable is sampled on, every variable you look at, be it discrete or continuous, is being measured on people or your subjects. So this is about how you actually sample your subjects. This is different from this is different entirely from this is different from your variables themselves, basically. Yeah, this is like a machine basically of some sort, right? That makes it easier for randomization. Like you, and in fact, we would use R, I guess, right? We probably would use R if you wanted to actually generate a random sample. But when you put your hand in a pocket, if your class is getting very big, you wouldn't want to select in a way that you systematically pulled up one group more than the other, because that's not random based. It's like a lucky draw, someone said. And if your draw is in some sense biased, that's not lucky at all. It becomes systematic. Whenever you notice a systematic pattern, that's biased, right? So we had to keep in mind that this becomes a biased sample, and then you've lost representativeness, right? So I'm going to stop here because you can see that if I want to continue on, I'm going to use R, and I'm not going to do it here. So I'm going to stop, and the quiz will be based on up to slide 32. And then next week I will finish off the last 5 slides, and I will talk about week 2 content. The quiz will open on Tuesday at 12 p.m. Yes, exactly. So after saying, once you open the quiz, you have half an hour. So please don't open it until you're ready. But it is, because of time zone differences, it's open for 24 hours. But you should not open it until you're prepared to write it, because about 10 questions. So every quiz will have around 10 questions, right? And half an hour to write them. They're all multiple choice, by the way, right? Just keep, they're multiple choice or matching. They're not short answer questions. They're either multiple choice or matching, right? So you can expect either multiple choice questions or matching questions. They're not short answer questions. Yeah. So the quiz will be based up to slide 32, and I'll finish the last 5 slides next week with week 2 material. Yeah, so it's not going to cover the material that we didn't see in the end of the slides. That wouldn't make any sense. Okay, cool. So let's stop here. Have a great weekend, everyone. See you guys next week. And don't forget to submit your tutorial worksheets by the end of Friday at 9 p.m.